My name is Karl-Erik Orsén, and I'm one of the professors here at the department, and my area is real-time systems, real-time control.
And my name is Martina Maggio. I'm also a professor here at the Department of Automatic Control, and I do research at the intersection between computer science and control theory.
My name is Johan Eker. I'm professor in real-time systems. I'm also a principal researcher at Ericsson, and I focus on control of large-scale compute systems, such as cloud systems or 6G telecommunication systems right now.
Our group is working on autonomous real-time systems, and by autonomous we mean a higher level of automation, essentially. Systems that have more power to make decisions and act than what an ordinary automation system has. By real-time, we mean systems that have to meet a deadline. It's not enough that the computer calculates the correct value, but the value has to be there at the right time, before a deadline. In this group, we work at the intersection between control and computer science, especially focusing on three different topics. The first one is how one implements controllers on very resource-constrained embedded devices, devices that you find in a car or in a mobile phone or in a camera, for instance. The second one is how one implements controllers up in the cloud in some data center. In that case, we have a lot of resources, but we have much, much more uncertainty. And then the third area is control of the cloud. If we're going to implement a controller in the cloud, we want to have an as deterministic and predictable system as possible.
We are here at the Automatic Control Department in Lund, and I'm here to show you a bit of what control means, at least for me. If you look in front of me, there is what is called a fruta pendulum. This is an inverted pendulum that we want to control and keep in the upright position. The same type of modeling and control system is what you find in a cruise control system for a modern car. And the same exact type of modeling is what you find when you want to control a Segway. If I execute the controller for this system, we can make it stand upright. And this is a very simple control example, but it actually illustrates all of the complexity of control. If you see, if I poke the pendulum, it has to come back up, and it has to do that in a reliable way. In real life, this corresponds to disturbances like the slope of a road. So for example, when you go up, you need to have more power in your motor to keep the same speed. And this is exactly the same as me poking this pendulum. I'm shifting something mechanical in the system, and I'm trying to make my system robust and resilient to these changes.
Okay, right now we are at Ericsson in Lund. And the reason we are here is that we collaborate quite a lot with Ericsson in the cloud control area. So what we're going to see here is a data center and also some of the base stations and compute stuff, which we use in our research projects. So we do control over the cloud. We're going to put the controllers in the cloud. You have the antenna part, you have the radio part, and you have the baseband processing part. The computations, the control computations, they will be done somewhere in a server in some data center somewhere in the world. And when we do that, we get additional sources of latency, communication latency, computing latency, which we have to handle in some way. So that is what we try to do with control techniques, better ways of implementing the controller so that they are robust and resilient towards this. In this case, the network processing is done in this box here. And this is exactly the same thing that you see in the data center.
Okay, so right now we're in the Ericsson Research Data Center, and at the heart of every data center we have servers, and the servers are organized in rows, and here we have a rack of servers, and besides compute power and servers, we also have storage, which is massive sets of disks where you can store your cat pictures, and here we have lots of disks which are easily removable and insertable. So in this cabinet here we have some high-powered GPUs that we run for our machine learning and AI activities. And all the servers and GPUs and storage you just saw in this row generates lots and lots of heat and needs to be cooled down. So in this data center we have 4 cooling equipments. This is one of those. And those guys also consume a lot of power. So the control come in the picture because we can place the workload maybe on this server or on this server or on this server having smart algorithms. We can also use control theory to have the set points to the cooling equipment, using traditional PID controller or some smart model predicted control or even reinforcement learning.
So for someone to do research in automatic control nowadays, there is many competences that are needed, and we need a mix. We need someone who knows about physical modeling and to create the models that we need for control. And of course, we need someone who knows about linear algebra and classical control techniques that we can use to guarantee something about the control systems.
Yeah, and nowadays, we also use machine learning and AI to develop new control techniques. And of course, competence in cloud is very important in the field that we are exploring.
And basic computer and operating systems.
Absolutely.
Control is everywhere nowadays. If you look at our infrastructure networks, then they are run by control. So look at trains, look at airplanes, look at autonomous cars, and also just normal cars with cruise control.
Yeah, and nowadays they're getting connected via the cloud. And this interaction makes things, increasingly complex. And that interaction needs to be addressed in the future control systems.
And we need to make sure that this way of addressing it preserves the fundamental guarantees that control offers for these systems. So ensuring that our safety as passengers of a train is preserved.
Yeah, and that those systems are always available and reliable.
Oh my God.
Bra, Martina.
I think this was